Now that you've seen some of the basics of genetics, we're going to go through some monohybrid crosses, which is just for one trait, and some test crosses where you can try to figure out what an unknown parent is. So for example here is some corn. Not the type of corn you normally see at the store. We've been breeding our corn and modifying our corn for so long to try to get it to look the same, but this is corn as it was in its natural state, and you can still find this some places. But you'll notice that each kernel, like this one and this one and this one, are their own seed, which means that they all have genetic information from their two parents. And so corn like this is very good to study because you've got many offspring here from the same two parents, and we can look at some of those genotypic and phenotypic ratios. So just to simplify things, I've made a picture here in the kernels, and we've got the black kernel, which is dominant, and the yellow kernel, which is recessive. Notice we are starting with two true-bred corns here, and when they cross, as we know, you get one little b from here. There's no choice because it has two little b's. We get one big B from here, and our first generation is heterozygous, and heterozygous with the black trait being expressed since that is the dominant trait. As we've seen before, when we cross two heterozygous, we can use our FOIL or we can use our Punnett square to predict what it's going to look like. And over here in the corner is the Punnett square to predict that cross. And as you can see, our genotypic ratio is 1 to 2 to 1, and our phenotypic ratio is 3 to 1. And so we would expect 3/4 of the kernels to be black and 1/4 of them to be yellow. And if we notice, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 by 3. So these have 45 kernels each. And in this case, it might be easier to count the yellow. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 yellow and 34 black. And you can see that's about a 3 to 1 ratio. Now when you're crossing different plants, we always know the genotype of the recessive because it has to have both recessive alleles in order to exhibit that trait. What we don't always know, however, is if the dominant is true bred or not. We know there's got to be at least one big B, but we don't know if it's big B or big B little b because those both have the same phenotype. So if you're going to do a test cross, you will always be testing a organism that is expressing the dominant trait, and you always cross it with a recessive organism. And then we can look at the ratio of the offspring here to try to figure out what the parents must have been. And so in this case, once again, we know there's 45 kernels, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 yellow. So we have 23 black and 22 yellow. So that's about a 1 to 1 ratio. But we can go back to Punnett squares and predict what must this parent be in order to get that type of ratio. Here are the two possible Punnett squares we have. Notice we've got the recessive from our recessive parent, and then we know that this dominant one can either be big B little b or big B big B. And so if we look at the traits here, we can see that if it were big B, all of the offspring would be black. And if it were big B, little b, half would be black and half would be yellow. And if you remember, we had a 23 to 2 ratio there. So this would lead us to believe that that question mark up here at the top is a little b because they're half and half. In fact, it has to be because if they were both big B's, it would be impossible for there to be any yellow ones produced. And so that's what we do with the test cross. You take your organism expressing a dominant trait, And once again, we don't know if it's homozygous or heterozygous. That's what we're testing. And you cross it with a recessive organism, and you'll be able to figure out if it is homozygous dominant, or in this case, heterozygous dominant. And so this is kind of how the test cross works. If we had a homozygous, this is like what we had earlier in the very first example. We know that all the offspring here would be big B, little b. And we've got the recessive here, and then half the offspring here are big B, little b, and half are little b, little b. Now, one of the things I wanted to point out here is you can cheat when you make a Punnett square. We did the Punnett square on the previous page, where you took the two little b's from the recessive and the big B, little b from the dominant, because these are the two possible alleles you'd get from there. And we found that it was big B, little b, big B, little b, little b, little b, little b, little b. Well, the fact of the matter is, if you wanted to take a shortcut, and if you don't feel comfortable taking the shortcut, that's fine. We can go back to this and we can say from the heterozygous parent, we know we'll get a big B or a little b. From the recessive parent, because it is homozygous, we know we'll only get a little b. And so you can have more of a Punnett rectangle if you want. Big B, little b, little b, little b. And it's still the same 50-50 ratio or 1-to-1 ratio. It's just a way of making it a little bit simpler if you want to. So if you have a homozygous parent, you can, in your Punnett square, kind of cheat and just do, well, that's the one allele they're going to get, and that's all they're going to get. Or if it's heterozygous, you do have to list both options on the side there. So that's just a quick little trick to cut some corners if you really understand what's going on. And once again, if you don't, then please feel free to go with the full Punnett square or the full FOIL method just to make things easier. But that is all for our test cross and monohybrid cross lesson.